Hi everyone. For section 2.3, I'll be splitting the videos up in 3 different parts. So this is the first part. We'll go over the concepts and the ideas behind calculating limits. And then in the second video, we'll go over limit calculations, slightly more basic ones, but still some tricky algebraic stuff in there. And then in the third video, we'll go over what to do when we want to calculate limits for absolute value functions. All right, so like I said, we'll start with the concept behind calculations of limits. You should have noticed that in section 2.1, we were focusing on the average velocity and instantaneous velocity. In section 2.2, we moved to the concepts of limits. So that was basically visually and graphically finding where certain functions approach, meaning finding the y values that they approached. In this video, we'll talk about looking at those limits. So what a function approaches, what the y value is computationally. So section 2.2, we got the visual idea. Now in section 2.3, we'll get the computational idea. All right, so for this section, if we're getting the computational idea, we need to know something called limit laws. Essentially, what we do when we calculate these limits is we look at algebra, so we need to remember some algebra, and we look at the limit laws. The limit laws that we have are all listed here. These can be found in your text as well, but it's basically laws and rules that we get when we're trying to calculate limits. I'm going to go over each one of these briefly, so I'll walk through them, I'll talk through them. You can, fast forward, keep it as is, do that how you wish, but I'll go over each property and then I'll give some of the reasoning. So I'm not going to do formal proofs of every single property, but I'll at least give you a computational idea. You can find formal proofs online if you want to, but I think it's just really important to remember that these limit laws stem historically from mathematicians who have really went in depth with them and proved them very formally, and so we know that they're true. What I want you to be able to do is at least just think of conceptually why it makes sense that they work. So I'm not going to have you formally prove everything, but we should have an understanding of why things are actually happening. All right, so the limit laws say that we suppose c is a constant. A constant just means it's some number, and that the limit as x goes to a of f of x and the limit as x goes to a of g of x exist. If these things are true, then the following properties, aka the limit laws, hold true. All right, so the first property says that basically if we have two functions added, we can split them and run the limit separately. So I'll type that out too. Okay, so if two functions are added, you can take the limit separately and then just add those limits back together to get your full limit or your final answer. The same idea goes with, that should say subtracting. So the same idea goes with subtracting. Right, the next limit law, there are a lot of symbols in here, but it essentially means that if c is some constant, some number, and it's multiplied by your function, you can factor that outside of the limit and then just multiply it back through. All right, next concept is similar to addition and subtraction. If you have two limits multiplied, you can take the limit separately and then just multiply that final answer together. Okay, the same concept goes for if you have two functions divided. So if you have two functions divided, you can just take the limit of the top, the limit of the bottom, and then divide, your numerical results. The only time this wouldn't work is if your denominator is 0, and that's because you would get something that is undefined. Okay, next, if you have something of this form, so you have a function that's all raised to a power, you can run the limit through the inside of that, get your answer, and then just raise it to whatever your value n is. This works when n is a positive integer. So if you have a negative exponent, we should remember from properties of exponent that would actually drop that down into a denominator. So the same thing wouldn't hold true, but you could arguably just alter that algebraically. But basically for this, we need to make sure n is a positive integer for this specific limit law to hold. All right, next one, if you take the limit of some constant, c is just a constant number, it will always equal that constant. Okay, so that's no matter what x is approaching down here. If it's just some number, the constant pops out. I'm going to explain why in a minute here, but referring back to number 3 up here, this is exactly why you can just factor the constant out. It's essentially because the limit of the constant is itself anyway. So you can multiply it back in at the end and it doesn't impact the answer. All right, next, if you take the limit as x approaches a of x, so this x here matches this limit x, you'll always get a. I'll explain that in a moment as well. All right, continuing on. Similar concept here. If the x is raised to the n power and these two match, you can simply plug a in, or run a through is how we would say that formally. So the a goes in where the x is. All right, same concept if you have the the nth root of x. And just so you know, a square root, there's actually technically a little 2 for the n there. We just don't denote it mathematically. Cubed root, there would be a 3, fourth root, there would be a 4, so on and so forth. So this only works when n is a positive integer. It's important to take note of that. Okay, and finally, if you have the nth root or some root of a function, this property is just saying that you can run the limit underneath the root. So this is just saying you can run your limit underneath roots. Again, that's if n is a positive integer. Okay, so now I'm not going to go through every single one of these and explain why they're all true, especially not formally, but I think it's good to have an idea, and so I'll just explain a couple so you get the concept. All right, so let's start with number 7 here, and let's explore why that actually works, why it's actually true. All right, so I'm just going to draw out a quick graph. All right, so I drew a quick graph with a few examples here. So first, let's just look at the limit as x goes to -4 of 2. Notice that 2 is really a function, but this would really be the function y equals 2. So 2 is a constant, it's just some number. What this really represents is the function y equals 2. So if I plot that and look at it visually, since we've looked at visuals before, this would just be a horizontal line. So we should remember from previous classes that a y equals value produces a horizontal line. Now remember, when we calculate limits, you're always looking at the y value you're approaching. Well, in this function, no matter what, your y value is always going to be 2. It doesn't matter if your x is -4, like it is right here, your y value is going to be 2. If your x was 5, like it is over here, your y value is still 2, so it's always 2. Right, the same thing happens if I have, say, a 5 here. So this is really the same as y equals 5. If I plot that, 1, 2, 3, 4, 5, come up here, your y value is always 5. So the limit there is always, no matter what, going to be 5, just like the limit in this first one is always going to be 2. Similarly, if I plotted another horizontal line, say down to the negative part of the graph, so y equals -2, I'm still getting a horizontal line with my y value always being equal to -2, so I know that that must always be the limit. So for number 7, the reason that when you take the limit of a constant, it's always just that constant is because you're really looking at a horizontal line where the y value stays the same the entire time. Okay, so I wrote a quick description, well, kind of quick description here if you want to write that in your notes if you happen to be taking notes, but I'll move on to property number 8 now. So if we go up and look at property number 8, it says that the limit as x goes to a of x is always a. So if these two match, why is it true that it's going to be equal to the value it's approaching? Again, we can look at this visually to understand the concept and the reasoning. So if we have the limit as x goes to a of x, right, thinking about x, keep in mind that this really represents the function y equals x, right? We know we have some function in there, or similarly, I could say f of x equals x. Doesn't matter how we verbalize that right now. Okay, so we should know that's just a basic linear equation, a basic graph. So the y-intercept is 0 there, because really it's x plus 0. The slope is 1 over 1, so we can make points, and we can create a line. So let's put that line in there. All right, now let's play around with this and see what happens. So let's say that we decide we want our x value right here to be a 2 instead of an a. Right, so if I go to x approaching 2, so as x approaches 2, 1, 2, I can see that my y value is 2. We can keep going through this. So let's say we want the x value or the x to be approaching, I don't know, -4. -4, right? So if I come over here and x approaches -1, 2, 3, 4, see what the y value is, you get -4. So that would be a -4. We could keep doing this, and since we have a line, you know that your x value is always equal to the y value. That's exactly what that says right there. So since your x is always equal to your y, then it's simply going to approach that y value, which is the same as the x value every single time. Okay, I'll go over one more property and then hopefully we'll have the idea at least. Okay, so next property we'll go over is property number 8, and this is the one that says the limit as x goes to a of x to the n is equal to a to the n so long as n is a positive integer. All right, so a couple of examples that we can consider are where y is x equals 2 and y is x squared and y is x to the third. All right, so if we look at this first piece with the function where y is equivalent to x squared, if we take the limit, if we take the limit as x goes to 2, right, we can see that in the graph as x goes to 2, 1, 2, our y value approaches 4. This makes sense because when we run that through our limit law, we get 2 squared, which is 4. The same thing would happen if we take the limit as, say, x goes to -1. Okay, if we had a -1 here, squared, we expect that we would get 1 looking at this graphically like we did in section 2.2, going to where x is -1. My drawing's a little off scale here, but we can see that that function approaches 1. So that is in fact equal to 1. Similarly, we can come over here to our cubic function. If we take the limit as, say, x goes to -1 of this cubic function, when we go over to the left one, we see we hit the y value of -1, so that's the same thing as -1 cubed, which is in fact -1. Let's test the other side. Let's take the limit as x goes to 2. If we look at this graphically, we'd go over 1, 2, that would hit where we have y equals 8. So we can see that the limit as x goes to 2 is really 2 cubed, which is equal to 8. So basically, instead of drawing these out every time, or instead of making this large proof every single time we make calculations, we can follow these limit laws. I know that I didn't go through every single one of these, but the concept is exactly the same. You could draw infinitely many pictures, you could do it computationally, you could prove it, and these would always hold true, which is why we're allowed to use them for our calculations. Okay, so that takes care of a lot of the reasoning behind this. In the next videos, I'll show how to go through this computationally and then how to look at it if you have, for say, or something like the absolute value function.